but since few of you are already here, I'd like to kind of get to know you. How many of you are currently having stream processing solution running in production? Okay, a few of you. How many of you actually like the framework you chose? I mean, whether you're using Storm or Spark or whatever, how many of you are really happy with your choice? Fantastic. How many of you are here to make sure that I'm not talking crap about your favorite stream processing solution? So I'm going to talk about very general patterns. So I'm not actually planning on evaluating or telling you you should be using this solution versus the other. More about general architectural patterns of how you should do things. And I'm going to show how those patterns apply if you use Storm, Spark, or Flink. So which means that since I'm covering 3 engines, it means that I only left out about 5 trillion of them. So if you're using, I don't know, data torrents or stream sets or Google new data flow or whatever, I'm very sorry that I don't get to talk about your favorite solution. I'm sure it's a very valid solution. There's just so many hours in a day. How many of you are using Storm? Fantastic, cool. How many of you are using Spark streaming? No, okay, 1. Okay, that's cool. How many of you are using Flink? 0, okay. I guess everyone will learn something. How many of you are using none of the above? Just either you made something up or you got a streaming solution from some other vendor. None, okay, so you either use Storm or you're the one person using Spark streaming or no streams at all. Okay, that's pretty good to know. So we still have 5 minutes. I figured I'll be fair to everyone who is still looking for the room and not start early, even though I have way more than enough slides for 40 minutes, and I like taking questions as well. In general, the rule for questions is just whenever you have a question, raise your hand and ask it. And I like answering, so I'll figure out how to cut stuff from the end to make sure answers actually fit in. I'm going to do a selfie. good meeting you in person.
I just had one request. In the end, given there are so many Storm users, can you just ask them that they can meet me outside just to get some feedback from them?
Actually, yes. Can I say it right now?
Oh, sure. Yeah, no problem.
Hey, everyone. Here is Parse. You're on the PMC of Storm, right?
Yep.
Yes, he's in the Storm Project Management Committee, and he's also a fantastic contributor to Apache Kafka, where we work together. And he'll be around after the presentation if you have any Storm-specific questions, which obviously I cannot answer to. He's the right guy to talk to about Storm. Thank you. And thank you. Okay, it's 11, and because we have 40 minutes and I have like a gazillion slides, we'd better get started. Okay, I'll wait for people to take their seat, and then I'll better get started. Okay, I think we're good to go. So this presentation is about general architecture patterns if your project has to do batch processing and streams, and we'll start with whether you even have to do batch processing and streams, and if you do, what do you do about it? I'm not going to get into a lot of details about any specific stream processing engine. I'm going to mention how some of those patterns look in popular ones. So we picked Storm, Spark Streaming, and Flink, basically because it's very easy to illustrate what I want to say using them. If you use something like Data Torrent or Google Dataflow or whatever else you use, if you wrote your own, those should A, still apply, and B, I don't mean that your choice of engine is wrong or not important. I just had to pick something. So let's get started. Okay, this is not working. How am I supposed to change slides? Someone doing technical stuff in the back. Okay, cool. I guess it is now working, or? No, it's still not working. Should I just tell you next slide, like the Larry Ellison thing? Okay, fantastic. I get to be Larry Ellison. So we're going to talk a bit about why do we need both stream processing and batch architectures, and what are the problems that happen if you have both. And then we're going to talk about some design patterns for stream-only processing and some of the technologies you can and should use for more Lambda architecture when you have both streams and batches. Next slide. Fantastic. That's me. I'm an open source contributor on a bunch of projects, basically working on things that bring data to Hadoop. I also tweet about a lot. I spent a long time doing ETL processing for many companies, mostly in data warehouses until 2 years ago where I joined Cloudera and started moving data around for Hadoop. And I wrote a book about a lot of design patterns. A lot of what I'm talking about is actually in the book. There's 2 chapters in the book about real-time processing where you can find a lot of the content for this presentation. Next slide. Okay, and another next slide. One more? Awesome. So we're going to, when you talk about batch processing, there's like a very generic pattern of batch processing. You assume the data is already stored somewhere. It can be your data warehouse, or it can be Hadoop. You're going to read very large chunks of this data, do something to it in very large chunks, and store the result somewhere else. That's like the classic ETL pattern. Pretty much everything you do in batch processing is like that. Next slide. So some examples is analytics, and I'm talking about business analytics of the type that how does our sale this quarter perform against the same quarter last year. A lot of the ETL is batching, obviously. A lot of machine learning, and there's a bunch of financial stuff, like value at risk, that the models pretty much only work when you have, now it's gonna work? Fantastic. When you are working in a batch mode, you cannot really do it on an event-by-event basis. So there is a bunch of those. And then stream processing, there is also kind of same pattern, right? You're listening into incoming events, so instead of waiting for the events to be written to disk somewhere where you can read huge chunks of them, you're just listening into events, do something with each event, and maybe store the result somewhere. Sometimes you don't even store the result. Sometimes you just trigger an alert or send back an answer, and you're done. So those would be things like anomaly detection. You swipe the credit card. It's a bad transaction. Flink, you have an alert. It can be things like monitoring and SLA. A lot of operational intelligence is done in streams. You cannot really wait until the end of the day to figure out that, hey, those machines are down, and this machine is at 90% CPU. There's a lot of dashboards and like more lightweight analytics that can be done in real time. And then there is also a bunch of ETL that is being done in real time as well. So the big picture is that you have streaming, you have batch, and you have those things that you can do only in streaming. So like alerts, you can only do in streaming on event by event. There is things that you can only do in batch, like the whole value at risk calculations. And then there's the things that you can do in both streaming and batch. So there's 4 categories. And the ones that is really interested in those that you can do in both. Because if you can only do it in streams, no problem, right? Only do it in batch, also no problem. If you have to do it in both, it's usually because the problem actually has 2 parts. There is the models that you train, and you train it in batches. And then there is something extra that you do, like respond to events, and you do it in streaming. 2 different applications, not a problem. It's those ETL-like processes that you can do it in streaming, you can do it in batching, that kind of present a bigger headache to us. And I'm kind of an old database person, so I speak mostly about ETL. And ETL, and really most of my customers who do stream processing do some kind of ETL-like thing with them. It's usually just few simple transformations. Maybe some kind of type conversion, field extraction, some kind of a lookup, some kind of a small aggregate, that kind of thing. It's usually there's very little rocket science done in stream processing projects. So you have this kind of ETL that you can do in either batch or streaming. And you have the question of how do I pick? And when you look at, okay, what is batch good at? Batch obviously is very efficient, right? There is natural overhead for processing every event. You use some CPU, you send the packet over, you have to get a reply, you have some network and disk throughput. If you write to a database, there is a bunch of locks that you have to manage. So in general, if you do something in batch, you have less of this overhead. It's amortized over more events. So batches tend to be more efficient. Also, they're easier to manage, right? Something went wrong with a batch. It's easier to reprocess. It's easy to debug a specific batch, see what went wrong, see the logs for this specific batch of events. It's kind of just something that's easier for us to work with. We have more tools. We have more experience. People have been doing batch processing in data warehouses for the last 30 years. We know how to do it. Streaming, on the other hand, has exactly one benefit, which is that it's very, very fast. It's almost real time. It's something, it gives you the answers you need and the information you need in seconds to milliseconds. So even though it has all those drawbacks, we still want to do streams because that's the only way to perform what we actually want to do, which is get information in real time. So lesson number 1, if you don't have the requirement to do something in real time, don't bother with streams at all. It's not efficient. It's harder for you to do. If there's no business benefits, don't do it. And one nice story is that we go to customers and they say, oh, we need to have this in real time. And I say, fantastic. How long is real time? How much time are you willing to wait? And they say, oh, it has to be really, really fast, like 15 minutes. Well, yeah, 15 minutes is not really, really real time. and you can still do batching in 15 minutes, even if you have like 1 to 5 minutes, it's still not real time. So figure out the requirements and don't bother with streams if you have a choice about it. So now suppose that you decided that you really, really have to have streams. What's the problem? Well, as developers, there's a bunch of things we really like. We like being efficient. We like it when things scale. We like it when we can recover from errors, things like machine crashing, but also our own errors. When we write bugs, we want to be able to survive them and not get fired and not lose a lot of money. We want to be able to experiment with a lot of different approaches without a huge process and career-risking discussions around it. We like debuggers, and everyone likes cookies. There is also things that we really don't like, except not getting our cookies and coffee in the morning. We really, really don't like having to maintain 2 applications that do exactly the same thing. The reason we don't like it is that it's a matter of about 10 minutes before those 2 applications that do the same thing are 2 applications that do slightly different things, and you have to go and explain every time why they're doing things slightly different. Okay, it's cut for you as well. I'm sorry about that. So the question up there is whether you really need to maintain the same app twice. And sometimes you do, and sometimes you do because of a requirement problem. You wrote the batch processing system, and then someone went and told you, oh, we also need streams, or you think you may need both for some reason. Sometimes you need both for for efficiency. You need to be able to take large batches of the data and do whatever you did in the streams, do it again, but very, very fast and very efficiently, which the second is actually a legit request. But sometimes you really don't need to maintain the same code twice. Sometimes you don't need it because it's actually different apps. You want to do 2 different things in batch and real time. We talked about it a bit. And there's also some misconceptions. Sometimes you say, okay, I cannot reprocess with streams, so I have to have batch. No, that's not true. You can reprocess with streams. I'll show it to you in a moment. You can even correct errors that happened in the past using streams. I'll show it in a moment. And you also, if you really, really have to have both batch and streams, there's a lot of systems these days that will allow you to maintain 1 code base for batch and streams, and I'm going to talk about that in a moment as well. So we're basically going to talk about all those things that sound like they force you to have 2 different systems, but you really only need 1 of them. So we'll start with some design patterns for stream-only architectures. Also, they got popularized as Kappa architectures for some reason, so you may like them with that name. And we'll go over a data warehouse example, because again, I'm kind of old school about things. And the way data warehouses typically worked, and they worked that way for the last 30 years, is that you had an OLTP database, or sometimes other sources of data. And you used to load the data in batches, usually once a day. You dump everything to file, and then you'd load them to a staging table, you do some processing, and you'd write them to your data warehouse. And everything about the whole tool set is very optimized for batch processing. If you talk to Oracle about their data warehouse, they'll say, oh, yes, we have external tables for batch loading. We have partition swapping for batch loading. Everything is very much optimized for batch loading. We're optimized for large scans. You don't need a lot of indexes. If you have extra data, just drop every single index. It will perform better. They have a lot of stories around this kind of thing. But then, obviously, business came along and said, oh, we have this requirement for doing things in real time. Those are actually very important to us. So what everyone did, and this is kind of out of the Kimball book of data warehouses, if you want to add real time, you add an additional real-time fact table, and you start dumping in data in real time to the real-time fact table. This table is basically identical to the partitioned storing 3 or 13 years of data fact table that is the real data warehouse, except it's significantly smaller. And it has the exact same dimensions, so you keep the same dimension tables and they are used by both tables. And the idea is that either you query just the very solid and known to be 100% true partition fact table, or you can have a view that also uses the real-time fact table. Once a day, the real-time fact table is partition swapped or rolled into the old fact table, and life continues that way. That's pretty much how things work. Note that in this case, you don't have 2 different applications. You have one application that does streams, and then another one that just does an occasional load, which is a completely different application. But the problem is that sometimes you get data wrong. Sometimes after 3 days of processing, you get data that is 3 days old that you need to reprocess, or you find that there was a bug in the old data. You have to reprocess a lot of data. And it used to be that you had to maintain 2 code bases, the one that does the stream processing, that's real-time and ongoing, and another one that you deploy only to fix data that got wrong and to reload all data into the fact table. And that used to be a pain because the code that does the batch processing was never maintained. It kind of diverged. It had its own issues. If you had to fix a bug, you had to fix it twice. You may have fixed it differently in 2 times. It was just a pain in the ass. So a better way to do it is to simply add another stream of data that will run in parallel. So you keep on updating the real-time table with the real-time information. But then you also have another, imagine this is Kafka. So you have a good, or this can be your OLTP databases, but it's way better when it's Kafka. You have a stable source of your information that you can read from. And you can also go back and read past information. So you can read the information that belongs to yesterday or 3 days ago. So you want to reprocess. You basically take another stream up, running the exact same code as the original. And it starts just going through all data and fixing the issues that it had yesterday, and creating replacement partitions as it goes along. Every time it created a new partition with the corrected data, you can just go and swap it into the partition fact table. Nobody will notice a thing. That's the magic of partition swaps. Once you're done, you're back to the old normal processing method. And this is good for testing out new algorithms. It's good for fixing algorithm mistakes, for, oh, I missed this, we only aggregated 3 countries. We are missing the other 2,500 countries. We should do something about it, that kind of things. So we can correct things as they go along. What you'll notice as a drawback of what I've shown is that over there, you actually have 2 applications running at the same time and doing the exact same thing. It's awesome for you as a developer, but your operations people may get cranky. They basically need the same resources twice. Are we keeping another cluster on the side just in case someone has mistakes? It can be kind of a problem. And obviously, there is overheads to doing real-time processing. Your business may be willing to pay those overheads if it's something business critical like getting real-time information, but they may not be willing to pay those overheads to correct past mistakes. Batch processing, as we said, is way more efficient. We may wish to correct past mistakes using a smaller system that is doing batch processing, in which case, Lambda architectures for the win. Those are the architectures where you do run this exact same code, streaming and batching, and you want to do it with the same code base in order to avoid losing your mind. So let's talk a bit how to do it, and we'll start with Scala. I am a big fan of Scala, although people kind of ask me, hey, if we have Java 8, do we still need Scala? So you don't need Scala, but you really want Scala. It's an awesome language in ways that Java 8 is not there yet. Anyway, Scala makes distributed programming very easy in the sense that everything is a map or a reduce, or at least it could be MapReduce. And here's the familiar word count. I know you've never seen word count before, it's all new to you, but bear with me here. So we split lines to words. We say that each word appears once, and then we sum them up. And the reason I'm showing it here, obviously because none of you have seen this before, but also because I'm going to show how this code looks in 3 different stream processing systems and tell you that A, it looks exactly the same. So whatever stream processing system you end up choosing, you will end up with almost exactly the same code. And second is that this looks the same even if it's batch. I mean, here you have the source of the data. It's a collection. You don't know how big it is. You don't know if it contains data for an entire day or for 3 milliseconds. This could be anything. So the point I'm trying to make here is that you're going to use the exact same coding patterns no matter what, and therefore you may not have to care that much if something is in batch or streaming, as long as you have the correct framework to run on. So speaking of correct frameworks, this was supposed to be Hummingbird. I don't know what happened to my slides on the way to the Hadoop Summit. Hummingbird is a very nice abstraction layer on top of MapReduce, Spark, Storm, and now the new things that Twitter is doing, and I don't know what it's called, but you know what I'm talking about. Or they basically have a new stream processing thing, and I don't know what it's called. What? Heron. Okay, so I'm betting it works on Heron too, but the whole idea is that you don't have to care. You choose the right level of abstraction, and you no longer have to know what is running underneath. So apparently Twitter, unlike anyone else I've known, really, really liked MapReduce. And the reason they really, really liked MapReduce is because it's so simple. You have map, you have shuffle, you have reduce, it's type safe, and it has some nice abstractions of top, but you don't need abstractions because everything is MapReduce. And after a while, when you start thinking in MapReduce, the world kind of shows up like that. You look at people and you see, oh yeah, you map and then you reduce. It kind of changes the way you look at things. So the people in Twitter kind of missed this idea when they worked with Storm, and I guess when they worked with Spark as well, and they wanted to recreate the same experience. So they came up with Hummingbird, which is basically a multi-stage MapReduce pipeline. So you can do map, 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 reduce, map, map, instead of just the MapReduce, which is the biggest problem with the original. It runs on top of everything that moves, and it makes it very easy to combine batch and streaming results. So you say it runs on MapReduce, it runs on Spark, and then it runs on Storm. So you can switch where you run things. But even more important, the way they do reduce means that results that run in real time and results that run in MapReduce can actually be combined together without any logical mistakes to it, which is the big deal of Hummingbird. So the API is very simple. You have a platform, that's what lets you choose between things. You have a source of data. You get collections. You do transformations on the collections. You do some kind of aggregation on those collections, and you store those aggregates. And the main limitation of Hummingbird, which looked like a huge limitation when we first looked at it, is that the reduce phase has to be monadic. Now, everyone loves monads, I know, and everyone knows exactly what it is, except me. So I had to spend a few days trying to figure out what they're talking about. It's one of those things like DAGs. It sounds so impressive, and then you dig into it, and it's the simplest thing in the world. So monads are basically associative operations. I think it's transitive and not associative, and I got the slide wrong. If you remember from Algebra, for me it's many years ago. Most of you look like you just did it, pretty much finished the course yesterday. The idea is that you have a set of operations. So here we do 1 + 1 + 1, whatever. And you can place the parentheses in any order you want. So over here we combine those, and then you combine this. But we can really put the arrows in any way we want and still get the same results. That's what makes things monadic, and apparently, I think it's transitive and not associative. And the idea is that if you have this property of being transitive, it means that we don't really care how we divide the work when we parallelize. It means that you can have each plus run on a separate machine, or you can do larger grouping, and you don't really care, because it will all give you always the exact same answer. So the main limitation on Twitter's reduce work is just that the reduce operation has to answer to this specific API and implement those. Now, it sounds like a horrible limitation, except if you go to GitHub and look up Algebra, which is another, obviously it has a bird, so it's another Twitter implementation. It has every single thing you ever wanted to do implemented in using those specific monads. So if you ever wondered, suppose I just want unique values. Can we do a count of unique values as monads? And how do I implement it? I'm very, very, very far from being a data scientist. I don't really know how to do those things to these algorithms. Well, they have an NDV algorithm implemented as monads. So, and they have everything else as well. So it gives you a lot of flexibility. And you can see that the code looks super familiar. Once you go behind the platform and having a producer and a store, it's basically the same. You have the same flat map. You have the toward is what I used as split. And then you do a dozer mapping, and then you do sum. It's almost the same code. And you can run it. You want to run it on Storm? No problem. You want to run it on Hadoop using Scalding? No problem. We're all good here. So, and that's the main message, is that your code will end up looking almost the same, whether you use the batch, whether you use streaming. You just implement word count once, and you don't have to worry about it anymore. Let's move on to Spark Streaming, which does pretty much the same thing. Spark Streaming had this abstraction called RDD, which is, OK, let's take a step back. Unlike Hummingbird, which is an abstraction on top of a bunch of execution layers, Spark Streaming is its own execution engine, but it has a very high-level API to it. And those RDDs are kind of shared collections, sharded collections. So you have a collection of data. It can be huge, but no worries. You can split it between all those different machines. And you have the same type of operations. You can do map, reduce, group by, filtering, all of those. So that's Spark. Spark Streaming is basically taking the same Spark code you already wrote and you like and enjoy, and running it in a very tight loop over very small batches. So instead of having this big RDD you just read from disk, you have a receiver that generates very small RDD for you, a very small collection, every few seconds, and you can do your operations on those very small collections in a very tight loop. You can also do some aggregations in between using stateful operations. So when you look at Spark Streaming versus Hummingbird, it's kind of almost apples to oranges, right? Hummingbird can run on a specific set of things. Spark is its own thing. Spark doesn't have real streaming, right? I mean, Storm actually gives you real event-by-event stream. Spark does micro batches, which basically means that we run the loops fast enough that it will look like it's real time, but it's not, it will never be, or very difficult to get it to be event by event. It has its own execution model. It's more, because it's trying to solve a simpler problem, it doesn't try to run the same way on everything. It has some more flexibility than Hummingbird. So the reducers don't have to be monads. They can do pretty much everything that Scala reduce can take, pretty much any function that takes 2 parameters and extracts 1 parameter can be used. And it can also do some nice aggregations, and it can even use HBase as a state store for keeping the state. But the main thing is that those are very similar. The code will look almost the same. They both use Scala and functional programming concepts to scale what they do. So if you go and look at Spark code, this is Spark, and you can see that I'm reading data from disk. And the code should be very familiar. We split, we map, we reduce. You've seen it a few times already. And when I want to go to Spark Streaming, I basically change 2 lines of code, add a third. Note that the entire logic of what I do, if you can call word count logic, it may be an exaggeration, the logic didn't change at all, which means that you can encapsulate it in a function or its own library and call it 2 different ways, and nobody will care. I would almost go as far in saying that you can even run the same code using Hummingbird with very little changes to it. And then we'll see that Flink also look the same. So one of the main ideas is that once you go functional programming, it's almost all the same. So let's take a look at Apache Flink. That's the last one in the collection. Again, it's doing kind of the same thing, only it has a completely different engine underneath. Don't share a lot of details about the execution model. So if you talk to the Spark people, they want you to know all about RDDs and their lineage and how they do error recovery, how they do everything. With Flink, when I go to the presentation and talk to the people, it's like, it works. That's OK. Let's talk about what you can do with it. So the main things I found about Flink is that unlike, again, Spark Streaming, which does those micro batches, Flink is event-by-event stream. So all the events go one at a time through a pipeline. But they can still emulate batches. And the way they do batches is actually super cool. They basically have this idea of checkpoint markers that they can push down the pipeline and say that here we started a batch, here we ended a batch, and that's how it goes forward, which is kind of cool. I don't know how nicely it performs. I have my suspicions that it will still suffer from a lot of the overheads of stream processing, but I didn't test, so I don't actually know. That's something that, let's say that if I would consider going with Flink to production, that would probably be the second thing I test. The first thing is that it's kind of a new project. Does it actually run at scale without crashing? That's always the first question to look at. But again, you'd ask this question, whether it's Spark Streaming, Storm, Flink, whatever. And again, what makes everything similar is that the APIs look almost identical. And the one thing that is similar between Flink and Spark Streaming, and that Hummingbird cannot really guarantee because it doesn't control the underlying execution engine, is that both Flink and Spark Streaming can give you exactly once guarantees if you use them correctly. because they can they can fake batches, and they can say that if something went wrong, we'll just redo this batch from scratch. It's something that is possible to do with Storm, but not something that you can guarantee with Hummingbird itself. So how does the word count look? Well, again, it looks almost the same. This is the batch example. So you get text data, and then this is actually, val count is actually a function on the text. And at some point, you pass the function over, and you execute the operation. When you do streaming, you basically do the same thing, only you say the data will keep arriving from this host and port, and it will keep on running. So you more or less have the same code for both use cases. Here's my favorite solution. I'm kind of biased. I think that for most use cases, the whole stream processing thing is a lot of overhead with very little return for it. I'm sorry, I just insulted everyone in the room at once. But bear with me here. I'm very sorry. The idea is that in most cases when I talk to customers, they have big dreams about eventually having those amazing complex processing systems. But right now, the requirements are usually super simple. They have some small transformations, maybe a simple aggregate, nothing groundbreaking. And if the requirement, usually I say don't reinvent the wheel. But what if it's a very, very simple wheel? Maintaining like one of those cutting edge, those bike wheels cost $2,000. I mean, it's ridiculous. And then if something breaks, you have to take it to a shop, and it probably costs another $2,000 to repair them. This wheel I can kind of repair on my own, right? You kind of need a bit sandpaper occasionally or something. So it's not a very good wheel, but what if you don't need a very good wheel? So yeah, another instance of me losing my presentation. It says how difficult it is to parallelize transformations. Well, the thing about very simple transformations is that they're very simple. So let's think a bit about what we need when we do a stream engine. And we all need the exact same thing. That's the beauty of it. They're all the same. You need to get data, a reliable way to get data, and you need a way to partition your work. So if you add more and more things that do transformations, you can get more and more parallelism. You need something to do those transformations, and you need a way to recover from errors. So if something fails, you'll still get results somehow. And then you need to store the results somewhere. It's not exactly rocket science. But it used to be that partitioning the workload used to be very difficult, and that managing all those executors used to be super difficult. But the world changed, and it's not that difficult anymore. So first of all, if we're looking at where do you get the data from, you get it from Kafka. Pretty much any stream processing system in the world has as the recommended source of data Kafka. Why is it recommended? Because Kafka is super reliable. It's not going to lose data. It's super scalable. It will, if you lose a Kafka node, you don't care. And it actually allows you to partition the data automatically. So what you actually want to do is write your code as Kafka consumers. Kafka consumers subscribe to Kafka topics, where the data is ordered nicely. And they each take over a small subset of the Kafka partitions. If one of those consumer crashes, Kafka will automatically rebalance the work between all those consumers. So you actually get partitioning pretty much for free from the data in Kafka itself, which is really awesome. Another really awesome thing about Kafka, which is reliable and scalable, et cetera, is that it's really, unlike ActiveMQ, it supports a lot of different methods of reading from it. So you can read from it in batches. So if you need to suddenly batch process everything, you can run your code and tell it, please read 3 days of data from Kafka. It can be micro batches. It can actually give you event by event for your stream. So you can really figure out where is your comfort zone with all those. And Kafka can actually store data more or less indefinitely. So again, unlike if you use ActiveMQ and 3 days later you find a problem and how do you get the data again, if you use Kafka, 3 days later the chances are Kafka will still have the data configured correctly. A year later, Kafka will still have your data. The other part of it is what happens if something crashes or you need to add more resources. How do you manage the cluster? It used to be that managing a cluster was a pain in the ass. Now we actually have too many choices. People use Yarn very successfully. People use Mesos very successfully. There's Docker, there's Kubernetes. Everyone has their favorite. So just saying that, hey, I am Spark streaming and I only run on Yarn or only on Yarn and Mesos is a drawback, because what if I like Docker and Kubernetes better? So you really, writing your own also lets you use your favorite cluster management and your favorite tools. So basically, this is kind of how you do this app. You allocate resources and do task management with something. You read the data from Kafka at whatever rate is comfortable for you. You do your simple transformations. You write the results. Typically, it's either back to Kafka to another topic or to something like HBase. People try to write from streams to HDFS. I don't really get the benefits of that, but we can discuss it later. In any case, the app is super simple. And if your app really is super simple, why bother with Spark streaming, or Storm, or Flink? All of them still have their own ruts and issues, and you have to learn a framework. So I like not overcomplicating my life, and I kind of recommend doing the same. Just to sum some things up. So first of all, think many times if you really, really need the same code twice. Think even more if you actually need streams. If it's not a requirement, maybe you won't. When you choose any kind of solution, pay a lot of attention to error correction. Pay a lot of attention to reliability guarantees. Check that you can actually work with your code. Writing word count is nice, but try to write something and then debug it, and then walk through with the debugger. Try to figure out, do you understand how it works? If it breaks, can you find out what broke? Make sure you can actually maintain your own code. We see a lot of customers that built fantastic systems that they can no longer maintain or debug. That's really a shame. You want to be aware of the latency throughput trade-offs. I kind of hinted that streams can be inefficient. That's exactly where you'll see them. If you have existing expertise with any tool, obviously we recommend using something you know very well. And keep in mind that stream processing is about patterns. The code will look very similar regardless of how you implement it. So really choose something you like and enjoy and feel comfortable and gives you all the guarantees you need. And just make sure that your transformations are maps and reduce and maybe even monadic to make sure they scale well. I'm done, and I have about 4 minutes to answer, I guess, a question or two. Yes, Felix.
What is Cloudera's recommendation for data formats in Kafka?
Cloudera still recommends storing data in Kafka in the Avro format. We like Avro a lot because it has schemas, which means that you have producers and consumers, and they can agree on, people don't have to talk to each other to figure out how is the data stored and managed. Happy?
How does Cloudera recommend schema evolution in Kafka?
That's outside the scope of the presentation, but do you have a specific question about schema evolution, or just highlighting that Kafka does?
Well, let's say there's a customer starting a thread.
So we recommend using Avro. We don't have any, Cloudera itself doesn't have a solution for schema evolution, but when we work with customers, we try to find a tool that works for them. Okay, bye everyone. I'll still be around if you have additional questions.